Okay, so welcome back to class. We're going to actually take a little bit of a tangent before I get back to what I was just talking about. I'm going to walk through what you should be doing, just so you guys are all aware of it. We're in week 3, and we'll get back to all the binary stuff. We were already doing a few things in class before I started recording this video. But the first thing you need to know is, what do you need to do this week? How do you make rent? How do you make your money in this class? Well, you come into Blackboard, and half your grades placed on Blackboard. And if you're missing the lectures, you could come in here and click on lectures to watch. And that will bring you into week 1, week 2, week 3. If you click on like week 1 or week 2, since we've already had those weeks, you can see in-class lectures. So this is the lecture I gave in class. And at the beginning of these lectures, I'm going to try to provide a summary of what you should be doing in class. So you can check out those lectures. Also on this lecture page, which I got to by clicking that right there, you could click on Course Outline Lesson Plan, which has a bunch of links, which I think are pretty cool, related to the concepts we're covering each week. So, you know, I kind of just summarized, this is what I want to talk about each week. And sometimes I have links. Like this is a really cool video. We'll watch it at the end of class today, Make It Count. And Casey Neistat was a guy who did some really interesting stuff. And, you know, he basically just made videos. And then companies started hiring him to make videos since he made such great videos. Make videos. And he had so many followers on YouTube, they gave him money to make videos about their products. And so Nike famously hired him to do one, and then he just went traveling around the world with his friends and made a video of that, and said "Make it count" because that was their thing, and had these cool quotes. And so we'll watch that "Make it count" thing. But now Casey Neistat is doing a social media deal, and his social media deal, he is the founder of what company? Casey Neistat Company. And Beam, it's Beam. I don't know, you could check it out, but that's not it right there. And it's, how do we get to Be Me? Meet Beam. Where's Beam? I want to see the website Beam. Beam app, there we go. TechCrunch, Beam, BuzzFeed. I guess maybe this would be the website. Unless it's somebody else's website. You never know what you're going to get. I just want the logo. Don't show me porn, please. I can't see anything here. It's just dark. There we go. Yeah, this is it. So that's weird. I don't like that design. But anyhow, we'll watch that video at the end of class. So you could get to those links right there. And then, of course, in our class, we have assignments. And so you should be through all the week 1, all the week 2, and, rocket science here. Week 3, you should do the week 3 assignments, including writing a 1-page paper, 1 page or longer, I don't care, but at least 1 page, and detailing what you've learned the first 3 weeks. So totally casual, no stress. You don't have to use APA format or anything like that. Just tell me what you've learned. And the main point of this is to roll around in the material more, for you to sit there and, try to do it without looking at your notes. But if you need to look at your notes, look at them. And don't try to impress me. Who cares, right? Just write what you've been learning. So you might write, this is how computers work. Or you might write about computer remembering and draw a little diagram, if you can, with a little remembering areas. And it's just casual, So just in a conversational tone, share with me, this is how computers work. Or this is what I've learned this week. Whatever it might be. Maybe it's gratitude, or to not text and drive. Or, you learned that, whatever you want. So anyhow, what you've learned the first 3 weeks. And you should be doing your coding stuff with Code Academy. So I haven't been spending any time on that class, but maybe we'll look at that today. And then my IT Labs, everything you need. If you need the code for our class, some people have asked for that. It's right there. And this will vary. So if you're watching this video at a different semester, make sure you go look to see what your code is. And then inside my IT Lab this week, you should do Word 2013. Somebody tell me, which assessment? Number 2, because last week was number 1. Right, so you need to do number 2, Word number 2. And then you need to do exams. And you need to do quiz, since we're in week 3, chapter quizzes. You need to do chapter 3, week 3, chapter 3. Pretty straightforward. All right, so what we were talking about is we were doing a little bit of review about how computers work and what we learned last 2 weeks. And we talked about how computers work, which is the entire Halloween circuit switches coding schemes. And we were also talking about computer remembering, which is, there's registers, there's cache, there's RAM, also known as memory, also known as primary something or another. I don't even like to say storage because storage is over there farther on. And then we have secondary storage, which is a non-volatile, meaning the power goes out and everything in secondary storage remains. And secondary storage is also, we've got three categories. We've got magnetic, optical, and solid state. So magnetic's hard disk drive and tape, optical CD, DVD, Blu-ray, whatever, and solid state drive, flash drive, those types of things. Right? So those are the things we were reviewing. And I just wanted to show you a little program I wrote here. I was talking about programming being a superpower. Literally, if you learn how to program, worlds of opportunities are going to open up to you. So there's no better skill that you can learn right now except maybe becoming a doctor, right, or a surgeon or a nurse. In terms of employability, it's one of the best skills you could acquire. So if you have any predilection for this kind of stuff, and once you get into it, it's like, at first it could be a little bit challenging, but if you take a couple programming classes and you get good, it starts to become like, holy cow, this is awesome. Because you learn to speak the language, then you are able to get around, right, and do stuff. And knowing how to code is amazing. So I wrote a little program here, and I set hello world equal to a variable. So m is the variable I set it equal to. And whoops, I didn't want to show you all that. I want to show you this. There we go. And so m is equal to hello world. And then I say, hey, print m. And so you can see here it prints m and a little dash. That's what this is. Just print that string and then also print this next argument. I can pass in as many comma separated arguments as I want. So it prints the value of m, which is hello world. And I said, you know what, show me that as a bunch of bytes. That's basically what that says. It has special notation. It means a slice, which means just a list. And so here's a list or a slice of bytes. We call it a slice of bytes. And it's a 72, 101, 108, 108. Wait, 108, 108, and then LL. And those bytes, those numbers actually correspond to the coding scheme for those letters. And the coding scheme is called ASCII. And so if we go and we look at ASCII coding scheme on the web, I don't know if I showed this to you, right? But here is that's not a very big table. Bam, bam, bam.
I remember that stuff from the 90s in chat rooms. You would do it on the number pads. You'd get like upside down question marks and stuff.
So here's an ASCII coding scheme. And we can see the decimal representation. So there's different ways you could, represent decimal, hex, and oct, and HTML. Those are all, just different coding schemes for the same thing. And so the decimal representation is what we're looking at. And 72 is capital H. 72 is capital H. And lowercase e is 101. And lowercase l is 108. And so we had 72, 101, 108, 108. And so we're using, right, a coding scheme here. And that's a little bit, those are the bytes. That's the byte value. Well, then I said, hey, just show me the first letter. And that's what that little 0 means. Means I'm now going to get the index value of one. I'm going to take whatever's that position 0, which is the H. And you can see it gave me 72. That's what this line did right here. It gave me 72. And that's the number. And I said, what is that type? And so this is printf, and you give it a verb. And the verb there is %t, and that's just you look it up in a table for this programming language, and you say, oh, that shows me the type. And so the type of that is uint8. So it's an integer, and it has eight zeros and ones. It's a byte, right? And that's what a byte is. And then I said, you know what? Show that to me in binary, %b. And it gave me 1001000. Ooh, that's cool, right? It gave me all those ones and zeros. And unfortunately, I don't have a camera hooked up today because I totally want to draw something on the board. Bummer for people who are watching this online. I wonder if there's some way I could do it without doing it. So anyhow, 10001. Let me show you something. And this is totally cool. And I just got to think about how I'm going to do it. So I think I'll do it in my presentations for this class. And I'll do a new folder, and I'll call it OK. And I'm going to create this week 03 binary numbering. And so here's decimal, right? And let me drop in a table. First, I'll change page setup to landscape. Just give myself a little bit more room. And then I'm going to insert, I think I have a table, and we'll go across 10 places, and then we'll come down a couple. That should be enough. And here's the ones, and then here are the tens, and then here are the hundreds, and then here are the thousands, and here are the 10,000s, and here are the 100,000s, and here are the millions, and here are the 10 millions, and here are the 100 millions. I think I'm getting that right.
Mm-hmm.
Or does that become billions?
No.
And then billions. Whatever, millions. And so the way we represented this was like 10 and to the power of 1. Let me see if I could insert, how do I make that? Insert special characters. Those aren't the ones I want. I want like a to the power equation. Crap. I'm going to insert equation. Insert equation 10. And do I have an equation editor? To the power of 1 to the power of 0. And let me highlight that. And arrows, math operations, relations, miscellaneous, Greeks. Shift F6 is what you're thinking?
Yeah, shift 6.
Where's my power? There we go. X to the power B. Oh, I just had it, huh? 10 to the 0. There we go. Cool. And I can't really make that much bigger, but I'm going to copy that. Let me just make sure I could edit it. Oops. There we go. So it's editable. All right, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, nope, too far, 6, 10 to the 7, 1, 2, 3, 4, 5, 6, 7, 8. Let's just get rid of these, and we'll call this. Delete column, and we'll call this by decimal. This is the decimal numbering system. That's the decimal numbering system. And so if I have a number like if I have a number like 103, that means give me 1 100, 0 tens, and 3 ones. Because 10 to the 0 is 1, right? So that's how it's represented. Right, and that's 103. That's what it translates to. $100 bill and 3 $1 bills. Okay, can I have a, and these go from 0 to 9, by the way, right? That's how we get the decimal 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is weird because when you count, you're like, wait, I got 9. I used all 10 fingers. It always feels weird to go 0, 1, 2, 3, 4. Wait, 4? No, that's because 0 is counted. And that's why when you saw me accessing this index right here, I said 0 because that's the first character. So that's decimal, right? Everybody remember that? Look familiar? So that's 103 in decimal. Let's now look at binary. So binary is going to be pretty similar, except binary isn't using 10 digits. It's using 2. And why 2?
On or off.
On or off. insert row above. Let's make this row just like gray. There we go. All right, so this is the ones. Anything to the power of 0 is 1, right? And so down here, what digits could we possibly put? What digits could we possibly put here? We could put 0 through 9, because it's decimal. It's 10, DEC, dec, right? Deca prefix, what's that mean? Deca, des. Prefix des, 10, right? Binary. Prefix, nothing, 2. Phi, thank you. Phi prefix, 2. So we could put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 right in this spot. And it means, hey, we have 9 ones, or we have 3 ones. Likewise, we could do the 0 through 9 right here. Hey, I have 9 tens. You want to put 10 tens, right? Because you'd then just say, oh, you know what? I got 100. 10 tens would be 100. You carry it over or whatever. So right here, 2 to the 0, I could put either 0 or I could put 1. I have 0 or I have 1. I can only put 2 digits. Just like we could do 0 through 9 for decimal, we could do 0 through 0 and 1 for binary because we only have 2 digits, right? And same thing here, only 0, 1, 0, 1, 0, 1. So if I wanted to represent the number 103 in binary, how would I do it? That's my challenge to you. Use your pen and piece of paper. Better yet, the number 3. How do I represent the number 3 in binary? Write the number 3 in binary. Let's see who amongst you has had either pre-exposure to this or you're operating at a very awesome CPU level. How do I write the number 3 in binary? It's going to be just a bunch of zeros and ones. That's all you're going to end up with.
Oh. Still not right. I thought you said right there.
What is I don't know? I have no idea, Alex. I'm going to be the biggest loser in the history of Jeopardy, going for negative $800 million. Here's the number 3 in binary. Because here's my 2's, right? 2 to the power of 1 is 2. So give me 1, 2, and give me 1, 1. Just like if I said, hey, I want $11, give me 1 10 and 1 1. That's $11 in decimal, right? 1 10 and 1 1 is $11 in decimal. 1 2 and 1 1 in binary is $3. You got a $2 bill and you got a $1 bill. All right, so that's the 2's. What's 2 to the power of 2? 4. Fear. What's 2 to the power of 3?
8.
So this is 16's place. I should be adding S's to these. 32's.
2. Nintendo is the next one.
64's.
128.
128's.
256.
Yeah, 256, that's right, but we're just going to stick with 8. Go to 128. So if we have a byte, which is 8 zeros and ones, we could represent 128 different things. Right? Is that right? What's 2 to the n? 2 to the power of n. 2 to the power of 8 would be 2. Oh, I'm confused.
6 is the next one, right?
It's 256, that's right. We can represent 256 things.
Yeah, just double the previous one.
Yeah, because 128 would just be that. All right, so next question. How would you write 5? How would you write 5 in decimal? 5 in decimal. Dude, if you're struggling writing 5 in decimal, right? Don't make it too confusing. All right, like 5 decimal. How do I do it? How do I write 5 in binary?
2 and 1. 2 twos, 1 and 1. 1 0 1.
How do I write 7 in binary?
1 1 1.
7. How do I write 15? Go give me one of the mates. How do I write 47?
0 0 1 0 1
47.
1 1 1.
30. I got 132. I've got 1 8. That's 40. I've got 1 4. That's 44. I got 1 2. That's 46. I got 1 1. That's 47. How do I write 129?
1 0 0 0 1.
129 in binary. So if we look at this program and the letter H is 72 in decimal, in binary it tells me it's 100100, right? So that's I don't know, 1,000,001,000. So let's just, I'm sorry, I'm using the wrong terms here. It's 3 zeros. These 3 zeros. Well, hell, it's just 72. So how would I write 72 in binary? Let's just figure that out. Is 128 more than 72? Yes. Is 64? No. I want 164 and I want 18. That's 72 in binary. So 0, 1, 0, 0, 1, 0, 0, 0. That's 72. Here is, now I have this hidden, so now I'm going to show you all of Hello World in binary. That's all of Hello World in binary.
Wow.
Right? Those are the zeros and ones. Those are the ons and offs. Somewhere in my computer are stored to store this phrase, hello world. And a space character is in there.
Is that yellow thing?
Huh?
Is it that yellow thing?
No, it's just a line. That's pretty awesome. That's really awesome. It all comes down to on-off switches. How many people like that's interesting to you? And it's like, wow, that's some pretty slick stuff, man. It's all just like Halloween porch lights. Are you kidding me? And a bunch of coding schemes. That phrase right there, coding scheme, that's the foundation of computers. And the coding scheme we were just looking at is ASCII, right? So we were just looking at the ASCII coding scheme right here. You know, and space right there is 32, is space. So let's go back and see, where is that space? Let me turn this back on. That space is 32 right there. Right after H-E-L-L-O, H-E-L-L-O, 32, space. That's that little character right there. It's actually a character. That's amazing. That's very cool. And then the cool thing is you could eventually start to create things, create programs, you know, or, you know, this is the foundation of it, but, you know, you could take it and start to do art or start to make useful businesses. Like, here's a little website I made. Never finished it, but that's awesome, right? And I was going to have it where people could share curriculum. Or this one. Let's see if I have sound.
I went to Washington to solve problems. I went to Washington. In my line of work, I guess politics never stops. I guess.
It's kind of a joke. I want to update the people here. You can make stuff. All right, so one more exercise for you. Write down your age in binary on your piece of paper. Write down your age in binary on your piece of paper. Write down your age in binary on your piece of paper.
Zeros in there.
Oh,
Your age in binary.
Yeah. Is binary always going to be 8 places, right?
No, binary is just
It doesn't matter. It just depends on the
zeros and ones. And so you could have a, like UTF-8. So UTF-8 is a coding scheme which builds upon ASCII. So ASCII is limited because ASCII can only do 256 characters or whatever. And if you look at the ASCII table, if it's only based upon 8,
You were right first.
if it's only based upon 8, if it's only based upon 8 bits, you could represent 256 things. But in ASCII, it's only 127. I think the first bit's used for something else. I don't know. So ASCII is 127. You could store 127 things, which is fine for the English alphabet. Good luck with all the other alphabets in the world, right? And so they had to add more, a coding scheme with more bits. So if it was 16 bits, well, then it's 2 to the power of 16 things that could be stored. If it's 32 or 64, so ASCII is a 4-byte code, or UTF-8 is a 4-byte coding scheme, and 4 bytes is 32, zeros and ones. So it's 2 to the power of 32, which is that many different things which can be encoded, which is a lot, right? It's like 4 billion things can be encoded, and the first 127 characters of UTF-8 is ASCII. Right, so that stayed the same, but then you have all these other Chinese characters. Let me show you that page again. All right. So somebody, anybody not get it, raise your hand. Write your age in binary.
16.
Couple people?
8 and 16.
Okay, what's your age? 18. So I need 116. I don't need a 64, you're not that old, but I need 116. I need no 8s, and I need 1 2. A 16 and a 2, I got 18.
You have a 16 plus your
What was your age?
21.
So I need 1, 16, 1, 2, and 1, 1. 16, 18, 19, sorry. You're 21? 16, 18, 19, 16, 20, 1. 116, 1, 4, 1, 1, 21. Anybody else, their age? 22. So 116, 1, 4, no ones. A 16 and a 4 is 20 plus 2 is 22. 22? Right there. 116, 1, 4, and 1, 2. 17, 116, no 4s, no 2s, and 1, 1. 16 and 1 is 17. It's beautiful. It's genius. Now you understand this joke. There are 1-0 types of people in the world, those who understand binary and those who don't. Right? There's 2 types of people in the world.
At least at this point, we should know that joke. At least at this point, we should know that joke, considering.
All right, cool.
Yeah. Very cool.
So computers run on electricity. Electricity could be on or off. If something could be on or off, we could encode messages for what that state represents. And, like Halloween porch, on can mean come trick or treat, off can mean could go away. And we could create a coding scheme. If we have more light bulbs, 8, we could store 256 things, create a coding scheme like ASCII, ASCII. And we could start to store characters of the alphabet and then store those zeros and ones as people type on their keyboard and look them up, print them back out. All right, so we'll look a little bit more at that right now. So we're going to look a little bit at secondary storage today, and then I'll look at the key terms in the textbook, and that should be about time for us. But shifting gears a little bit, so get your gear shift in your head. Shift your gear in your head. So we'll talk about secondary storage, which includes magnetic storage like hard disk drives and tape. And it includes optical storage like CDs and DVDs. And it includes solid state storage like flash drives or solid state drives. And it's really hard for me to talk when other people are talking. I love that you guys are helping each other. You almost done, though? You helped her figure it out? Cool. What's your age in binary? In binary, not decimal. Read me the ones and zeros. Read me the ones and zeros. 24. Yeah, so your age in binary is 11000.
So that's how you say your age.
In binary.
1, 1, 0.
Yeah, my age in binary is 1, 0, 1, 1. That's my age in binary.
You're 39.
I'm 101010.
Are you 39-year-old?
Starting at the
I'm 44. 32 and 8 is 40, and 4 is 44.
looks like an anagram of your name.
All right, so talking about secondary storage. You guys ready? Or you could talk afterwards. So here's a hard disk drive. This is what it looks like. If you were to open up your system unit or your case or your computer, right? When you have a desktop, we call it system unit or case. You can see some cases or system units down here. You know, if you just Google system unit, for those of you who are online, you'll see images of these cases. Obviously, some of them look different, like the Mac desktop case system unit. Wow, pretty inaccessible, hard to get into. But this type of a system unit, definitely much more easy to access. What's up?
What's the difference between HDD and HDR?
HDD and
HDR.
HDR. HDD is hard disk drive. I don't know what HDR stands for. HDR.
Photo term.
HDR, what's HDR? High dynamic range is a photography practice that recently introduced to camera phones.
When you
So
overlay different photos of the same subject, and they're all different exposures, so you can have a lot of dynamic.
oh, trip out. I've heard about that. Right. So you could change your depth of field and stuff later in Photoshop. Trip out. So that has nothing to do with storage. From that, at least that look up at the acronym. All right. So this is your system unit or your system case. And inside your case, you could open that up. If you go around, just each one you got to figure it out. But you could just pop it open, and if you pop it open, it's going to look like that. And then inside, you'll see this thing right here, and that might be your hard disk drive. There's also like maybe a CD drive in that bay or DVD drive. Old computers will have a floppy drive. And then this is the fan for cooling the CPU. Here's your power supply. Your motherboard's right back here. Underneath this fan will be the CPU, right? These little holes are to allow airflow to come in and out. And anyhow, so that's your hard disk drive right there. And this is what it looks like. And if you were to cut it open, you would see this. And it has an arm and read-write heads, but it's not just a platter on the top. It's a stack of platters with read-write heads that read the top and the bottom. And what's happening is that read-write head is going across and reading magnetic charges. And those magnetic charges, if they're positive, they mean one thing. If they're negative, they mean another. I don't remember which is 0 and which is 1. Does this say? One way represent, particles lying one way represent binary zeros. The other way represent 1. So maybe there isn't standardized. I don't know. Anyhow, the read-write head floats really close to the platter of the hard drive. So there's the read-write head, that purple thing, and then the hard disk surface is that orange thing. And you know, there's the dust particle and the human hair there, and smoke particle. And so, you know, you want to, if your hard disk drive gets crap in it, it'll cause a hard disk crash. So the read-write head will actually run into that dust particle or that thing of hair and damage the surface of the hard disk drive. So hard disk drives spin at like 7,200 RPMs, 7,200 revolutions per minute. So they spin pretty quick, and you could have a head crash, but they're sealed, so crap can't get into them, right? Because computers usually get dusty on the inside. So those are hermetically sealed, like a hermit in a cave by themselves, locked away, right? Your platters are sealed inside the case. So that's a hard disk drive. The organization of the positive and negative charges, the zeros and ones, are in little, what do they call them, sectors. And so basically you have tracks, which just like down at the fairgrounds when you're betting on horses, running around a track, the tracks run around the whole circle. And then you divide those up into little pie shapes, and those are sectors. And then a collection of sectors are known as a cluster. Right, and so that's, you know, stuff gets stored in the sectors. I think it's like 512 kilobytes in each sector. Maybe it's bytes, I don't remember. I don't care, right? Details. Some details are important, some not so much until you need to use it and look it up. I just don't know that stuff. But anyhow, that's the kind of stuff. That's how it's organized. You basically have cubby holes into which you put zeros and ones, right? And that's pretty much how all storage, all memory, all remembering in a computer works, is you have cubby holes. And so if I was to come back to this program right here, and there's my variable m, and I'll just comment all that out because that's cool, right? I could do this. M is equal to, well, I'll put n is equal to, let me see if this works, and m format.print line m n. Let's see what that does. Cool. So you can see right here, I got hello world, which is the variable m, and then that's the memory address, which is a cubbyhole, basically, like a postal address box. Inside my computer's memory, in RAM, hello world is stored in that location. Whoa. Like, I just got the address where it's storing those zeros and ones in my memory. Like, that's pretty cool. And it's called taking the address. You could create variables that then point towards an address, and you could pass around an address in your program instead of passing around a lot of data, right, which might slow your system down if I'm passing around all 18 million user accounts at once, right? Well, that's going to slow my processing down. Let me just pass around the address where all that stuff is stored. So you could get the address and pass that somewhere to do something else with it. But that's cool. The idea here is that we have little cubby holes where zeros and ones get stored. And we could actually look up those cubby holes. And so that's same on a hard disk drive. We have these little cubby holes, sectors, where zeros and ones get put. And they have an address. And we keep track of those addresses with something called the file allocation table. And fat people. It's always interesting what comes up. Fat wallet, fate, Father's Day. And you know what? This says something about me. So it's always really kind of interesting for me when I watch videos of other people on their computers to see what their completions are, because it tells me about them. And that can be embarrassing sometimes, right? Because people might type in something and show you something else they've searched for, you know, that maybe they don't want you to know about, you know? And so, anyhow, I've shared that with you, and now I've got to go clear all my cache and never be logged into Google when I'm showing you these things. But I don't remember what I was going to show you. File allocation table. And let's just see if there's any interesting images. Well, I like that last one right there. So here's a file allocation table. It's not such a great diagram. And I'm at a crappy site. File allocation table, Wikipedia. Whatever. So basically, a file allocation table will be like, you know what? I got a couple of different cubby holes, 0 through 15 listed here, and you know, one file might be stored in these different cubby holes, 2, 3, right? And so it just keeps track of where zeros and ones are stored. So when I say, hey, go open up this file, it'll say, okay, well, it's stored in these different cubby holes. And then it goes to those cubby holes and gets those zeros and ones and then brings my file back. When you delete a file, like most of the time, what it does is it deletes the entry, but it doesn't delete your zeros and ones. So it deletes the entry in your file allocation table. It's actually called NTFS in Windows now, new technology file system, but deletes the entry in the table, but doesn't delete the zeros and ones on the hard drive. And so you might think, great, I deleted all of that evidence. It's no longer on my computer. No, all it did is it deleted the fact that there's a reference in the table to those zeros and ones. The zeros and ones are still on your hard drive. Those cubby holes where they were stored can now be overwritten. The next time you save stuff, they might be overwritten, but those are still there, those zeros and ones, until they do get overwritten. And so you could, on a Mac, you know, like if I go up to my Mac and I say empty trash, which you can see I do frequently. So I'm in Chrome. Let me go into Finder. Empty trash. I've got two choices on a Mac. And secure empty trash is going to write random zeros and ones. It'll not only delete the entry in the table that this file is stored in these cubby holes. When you need those zeros and ones, go to those cubby holes to get them. It'll not only delete that entry in the table, just keeping track of where all my zeros and ones are stored, but it'll also go to those cubby holes and then just write nonsensical zeros and ones over what was previously there. That's secure empty trash. It takes longer to do it that way. Gotta take a breath. I forgot to bring my beers to class. It's hard to keep teaching without having a beer. I'm sorry, did I just say that out loud? I'm just joking. I joke about this stuff, but for many years I didn't drink at all because I became a Buddhist, and I was just like, well, seriously, it's not a joke. But to be a Buddhist is to not be a Buddhist, which is what I like about Buddhism. It's like the belief of no beliefs. It's kind of wacky, right? Like they created an entire belief system based upon not having beliefs. And that if you're believing something, you're already wrong. It's like you're already farther from the truth. Because ultimately the truth is that it's not a conceptual thing that the mind created. It's the reality without the overlay of thought. We're always overlaying thought on reality. Oh, I like that. I don't like that. That's good. Oh, I hate that kind of stuff. And that creates suffering for us because we're always seeking what we like. Oh, I want more of that. And we're trying to get away from what we don't like. Oh, that stuff sucks. Those people suck. That kind of driver sucks. That pisses me off. Right? I'm a Republican, and I hate Democrats. I'm a Democrat. I hate Republicans. Jim's always playing Fox, and it drives me nuts. It's driving you nuts because you're putting over this overlay of thoughts over just sound, images, people talking. Big deal. Right? And when you get rid of those thoughts, those beliefs, you have peace. When things no longer need to be different, you're at peace. So it's the belief of no beliefs. So I totally got into Buddhism for a while because I'm like, wow, that's awesome, dude. I love the belief of no beliefs. And so I started going over to the Buddhist monastery right here on Clinton. You go past 99, you like hang a right after a couple of stop signs, and there's like this Cambodian Buddhist monastery. Cambodia, right here, and it's right there. So here's Fresno City College, right there. And you just go over there, and let's see if they have pictures. Oh, cool. Let's just see what else we got. Images. Yeah, that's it. So it's totally cool, man. And you could just go there and hang out, and the monks meditate every day, and you could talk to them and say, hey, when do you guys meditate? And they get together and they do this chanting, which is just like totally beautiful. And you just like sit in there and meditate with them, and it's like the craziest, like, I don't know, it's crazy. It's just beautiful, crazy, like very peaceful. And like if you do it long enough, your mind, you feel like your mind just gets totally blown. It's like, wow, I feel so high. I've just been sitting here listening to these monks chant. And you leave, you're like just all peaceful and blissed out. And so anyhow, I recommend it. Just go in. There used to be this dude, Walter, there, who I swear could read my brain. He'd like say things to me, like I'd be thinking something, meditating. He'd be like, don't be too involved with girls. Just meditate. I'm like, how do you know I was thinking about girls the entire time I was meditating? But Walter's not there anymore. He's some other monk. And I got married, so I haven't been going. I barely have time to do anything. And I gave up drinking for a long time. So that beer thing was just a joke. Because in Buddhism, it's like, don't take substances which obscure the mind. Face the mind directly for what it is. Don't run from it. Anyhow, just a joke about beer. And a little bit about meditation and Buddhism. But then I realized I was really attached to not, and it's all about don't be attached. And I realized I was really attached to not having beer, or a glass of wine. No, I don't drink. I don't have beer. I'm supposed to keep the mind pure. And then my wife's like, you're pretty attached to not being attached. I was like, oh, dang! Totally got caught by belief again. So I was like, all right, give me a beer. I'll also have some beer. It's all right. It's no big deal. So that's hard disk drives and file allocation tables. And here's, you could get fragmentation with your hard drive. So fragmentation is just basically your zeros and ones are stored in cubby holes all over the place. And when you defrag your hard drive, it takes all your zeros and ones that are related to a file and puts them close to each other physically on the hard drive so you could get them more quickly. So sometimes in Windows, people will defragment it. And you could just search for defrag Windows, right? And they'll show you how to do it. And you can see images of Windows defragging, right? So defragging your hard drive. All right. So secondary storage optical, we got to store zeros and ones. And the way optical media works is that a laser gets shined at it. And if the laser bounces back, it means one thing. And if it doesn't bounce back, it means the other. Right? And so we get the laser to bounce back if the surface is shiny like a mirror. And if it's not shiny like a mirror, it doesn't bounce back. And so we could have those be zeros and ones, right? And so the way we get it shiny or not shiny is we either have a shiny area or a not shiny area on the surface of the platter, and when the laser hits, it either bounces back or it doesn't. That's the basic idea, right? And it writes out from the center in a spiral. So when you burn a CD, right, writes out from the center in a spiral. So if you only burn a little bit of data, you could see, oh, it only burned a little bit, and the rest of it's all shiny, but the only right around the center is kind of dull. And then rewritable media, well, you could then change what was shiny to not shiny or what was not shiny to shiny. You could rewrite it. So it's just the technology properties of the medium which allow you to do that. That's the basic idea of CDs, DVDs, Blu-ray. And then we have solid-state storage, right? Still part of secondary storage. Also sometimes called flash storage, like all these memory cards or flash drives. And this was interesting. I just saw this online, so I was like, oh, that's pretty cool. All right, so it's just a bunch of transistors which symbolize zeros and ones, and up to like 3 terabytes or more now, I think, aren't they? I don't know. I haven't looked. Maybe that's not right. But anyhow, no moving parts means less energy needed and it's more robust. That's a really important part. So laptops with a hard disk drive, they have a platter spinning and they have read-write heads, so you don't want to bang a computer that has a hard disk drive. But a computer like this one with a solid-state drive, great. It's super fast. There's no moving parts. It's more robust. You bang it a little bit. You don't have to worry about a head crash. So solid-state drives are quicker and they're more robust, but they're also more expensive. Right? My friend calls flash drives virus sticks. Virus sticks. because if you plug them in, you know, one computer and then take it home and plug it in, you could get a virus. And that's a common way of infiltrating enemy networks, is to just get somebody to carry a flash drive into the network and plug it in and then have it secretly install a little piece of software. And there's a famous case of America hasn't taken credit for it, nor has Israel, but they're the only ones who could have produced it. But you could watch 60 Minutes. 60 Minutes and Virus, what the heck was it called? Virus, computer, 60 Minutes computer virus. It's called Stuxnet. Thank you. Thank you, Google. It's called Stuxnet, 60 Minutes Stuxnet, where we physically sabotaged Iranian, what do they call it? Uranium processing. And we were making all their machines crash that were processing the uranium. Ha 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 ha. Here's a solid state drive. And we just talked about the difference between a hard disk drive and solid state drive. And hard disk drive has read-write heads and moving parts and platters. And solid state drive is no moving parts, more robust, faster. Last thing we're going to talk about is input and output devices, I/O devices. So we already touched on this. Name an input device.
Mouse.
Keyboard, mouse. Name an output device.
Printer, screen.
Printer, screen, speakers, right? So it's just a way of categorizing devices. And remember, the 4 things a computer can do is IPOS, input, process, output, storage. So we're talking about the I/O. And we categorize devices by whether they're an I device or an out device. Sometimes you'll hear about I/O in computing. Like input, output is what we're talking about, right? And so here's a list of input and output devices. You could watch this video and pause it and read them, but it's just the stuff you've said, right? Monitor, printer, speakers, headphones, projector, output devices, input devices, keyboard, mouse, microphone, scanner, whatever. And you should know about right-clicking and scrolling and all that. So if you don't know right-clicking, experiment with it. And voice recognition is pretty awesome and powerful. So most of you have probably seen this, but many of you are surprised by it. When you click this little microphone, no thanks. I got to enable it. Search without lifting a finger when you say, OK, Google. But then it's always listening. Can I just click it? I can't. I got to enable it. Black dogs.
Here is information from PetFinder.
Whoa. Cornucopia of blackberries. Cornucopia of blackberries. It's pretty amazing. Cornucopia?
No,
That's-
what I just never really got is why does it say OK Google? Because you saw the press on the mic.
Dude, your voice totally sounded like the girl on Google. I was like, wait a minute. What? I was confused.
That's what I thought.
I thought Google's like talking smack. What's Google saying? What did you just say?
Why does it say you can say OK Google or click on the mic, but you still have to click on the mic just to say OK Google? Like,
OK,
if you
Google.
just say OK Google, it doesn't catch on. Like, don't press on it, just say OK Google. It's not going to go to the listening screen.
I think you had to press yes on that
Yeah.
question.
Yeah, don't press
So
yes.
whenever he says "OK Google," then it just automatically turns on without him having to actually press the mic. But since he didn't, he has to press the mic every time.
Dope. It's very cool. Voice recognition. Output. Monitors. Aha, that's a monitor. That's an old monitor. If you ever see one of these in the dump yard and you have a metal pole and you think this will be fun, I'm going to stick the metal pole into the monitor, don't do it, because those can maintain a charge even long after they're unplugged, strong enough to kill you. That's the only reason I show this slide.
I'm going to tell my cousin.
It's like
I know that there's a lot of y'all who live up in the hills.
like messing with an arcade cabinet.
We make up what's displayed on a screen. We already talked about this with pixels. Those are picture elements. They're a bunch of little dots which make up our image. So right now you're looking at a bunch of little dots, right? The resolution is how many of those little dots left to right, width and height. So 19 by 20 by 1080 means that there are 19 by 20 by 1080 means that there's, I don't know, 2,073,600 little pixels to make up the image for my screen, right? Those are pixels. And that's resolution, how many pixels, width and height. there's a bunch of different resolutions out there. If you Google resolutions, you'll see something like this, which shows you the different resolutions. You can see 1920 by 1080 right here, 1280 by 720. So these are landscape, right? More wide than high. And you can see like the different VGA, HD, HD 1080, HD 720, right? The different representations of what those things stand for. And that's known as 16 by 9 aspect ratio, right? 16 by 9 aspect ratio. So 16, for every 16 over, you go 9 up. And that's letterbox or movie screen. 4:3 is kind of like the old TVs, the old monitors, they're square. And then for each pixel, we store zeros and ones, right? So we got to say what color should that pixel be, and we can adjust the color of the pixel. So for each pixel, we got to store what color that pixel is going to be. So if I have a bit depth of 1, how many possible colors? If I have the bit depth of 1, so for each pixel I'm storing 1 binary digit, how many possible colors can that pixel be? Question, answer it. I'm using, if I have 1 light switch, how many messages can I store?
1.
1 light switch, how many messages can I store? 2. Come trick or treating or go away, right? The porch light's on or off. So if I am storing with 1 switch, which could be either 0 or 1, I could store 2 things. And it's usually like, you know, the old computer monitors.
The green screen.
You know, here this one is either black or yellow. Here, this one, it was black or green. Right? That's it. Because for each pixel, I was storing 1 bit of information. So that could either be green or black. So each pixel would be green or black. And that's known as bit depth or color depth. How many pixels for, how many bits of information I'm storing, how many bits I'm storing for each pixel. If I had a bit depth, a color depth of 2, how many possible colors could each pixel be? 4. Right? So 2 pixels, 4 possible. And so when you look at that, here are the different color depths. So 1 bit, I could have 2 colors. 2 bits, I could have 4 colors. Or 24 bits for every pixel. 24 zeros and ones for every pixel. I could have true color, which is 16 million, almost 17 million possible color combinations. So if I had a picture that was 1920 by 1080, and I stored 24 bits, I had a color depth or a bit depth of 24, I stored 24 bits for each one. For that one picture, I am storing 49,766,400 zeros and ones for that one picture. So that's bits. Well, let's find that in bytes. Come here. Just do the math. Why don't you do the math? Oh, because I did it like that. I needed times. Cool. It's 6 million bytes. Well, how many kilobytes? It's 6,000 kilobytes. Well, how many megabytes? It's 5.9 megabytes. Well, that's not that big of a picture. Right, but 5.9 megabytes is like what did I say, 49 million zeros and ones, almost 50 million zeros and ones. And that's 1920 by 1080 and a bit depth, color depth of 24. 24 zeros and ones for each pixel. It's kind of cool. So I just answered those questions for you. You could connect multiple monitors to your computer. So when I'm at home, I connect multiple monitors. So I could do one thing and see the results on the other. Did I show you Live Edit? I think I did, right? With WebStorm. Yeah. Where I changed my code and the web page changes. I showed you that? Yeah, I do that with 2 monitors. So as I change my code, I could actually see how it's changing the web page in real time. It's awesome. That's output too. And then we have printers. Dot matrix printers. We talked about this. Impact printers. Impact printers actually impact the page like a typewriter, or they're hitting pens against an ink ribbon, and that's hitting the page. That's an impact printer. And then you have inkjet or laserjet printers, and they are non-impact printers. So they spray ink. It actually boils the ink, and the bubble pops of ink, and it splashes on the page. Crazy, whoever came up with that. And laser printers do this weird thing with positive and negative charges, where your page gets charged either positive or negative, and it's flown through a cloud of ink dust with a certain charge. So the charges stick the ink where opposites attract, and then not stick where the same repels, and then it runs it through a little heater and melts the ink on. It's kind of nuts. And then you got different printers, but that's it. I/O devices and storage. So what we learned today, we learned about secondary storage and hard disk drives, and we learned about fragmentation, and we learned about optical storage, and we learned about solid state storage and all that, and I/O devices, input, output devices, pixels, resolutions, bit depth, color depth. So not a lot of phrases, but, and then maybe one of the most important things we learned today was just seeing this stuff. Right? Memory addresses, binary coding schemes, binary numbering system, figuring out your age. So you can watch this video to bring this back up. Anybody want this sheet here accessible from Blackboard? One person, that's it. Anyone with this can view it. So I will go to Blackboard, announcements. Oh, nah, I don't really have room. Great announcement, binary and decimal numbering systems. Right here, yo. There it is. You can click on that now. Anybody have any questions? I promised you guys a Casey Neistat video. I wonder what else he has out. We're going to watch one, but I'm just curious. We're going to watch the one Neistat. Different ones. All right, so we're going to watch that, but I got to stop recording. Any questions? How many people had your mind blown today? Cool. How many people did not have your mind blown today? Cool. How many people are going to go check out the Buddhist monk thing and see how high you could get? Cool. Just cruise up and say, could I meditate with you guys? And they'll be like, yeah, sitting back. Very thick Cambodian accent. All right. Anybody, no questions?